Okay, as current Mars Czar of NASA, Jim Watson, and I know, of course, that his job title is officially Director Mars Exploration, but that's a Mars Czar to me. He manages NASA's roughly 500 million a year Mars portfolio, I've been told. That sounds like a lot of money, but thinking opportunity, curiosity, Mars Odyssey, Maven, a Mars Reconnaissance Orbiter. I'm wondering how much money that really is, and I'm building a 2020 rover in the meantime. I would think it might sometimes be hard to find all the money to do all these things, and then we get the budget for 2016 on the books, and apparently NASA then says, Opportunity has been serving us for a long, long time, but the 24 or 14 million, I hear different accounts of how much money it is. Where do we find that? Because, we have to plan for new missions as well. And that's how it goes in any company, but also in NASA. Personally, I hope you will find the money for Opportunity, not just because I like the old broad roaming Mars, but also because I think after you spend so much money getting her there and doing all the science, if she still gives you viable science, I hope you'll find, a little money, because otherwise it's kind of a waste of all the money already spent on her. After all, getting her was probably the most expensive thing and the hardest thing. Jim Watson is going to share with us how robotic missions of the 2020s will pave the way for human missions in the 30s, and how I think doing so is giving us the best bang for our bucks. Jim will introduce his panel.
Thank you. Let me first thank you for that kind introduction, and just take the moment while I have the podium here to plug MEP, Mars Exploration Program, a little bit. You heard yesterday John Grunsfeld likes to say we've been at Mars. We've been at Mars for quite some time. Humans have been at Mars through our surrogates, the robotic systems that we send. I think he's trying to make a point that we understand a little bit about the system and a little bit about Mars, but also point out, and we never quite get to that in the conversation, that the MEP program has been doing for over a decade now, a little bit of what Firuz and some of the folks suggested this morning with the larger Mars exploration program, thinking about the longer term problem. This isn't a one mission kind of program or activity. This is a set of missions that build on longer term objectives, and we have to figure out how to do it within our modest budget and within the advocacy constraints, within the scientific integrity aspects associated that drive the program itself, the decadal priorities and other things like that. So we've been managing the infrastructure, the logistics, the objectives, the achievements that the program needs at the Mars system, in the Mars system, for quite a few years. So granted, it's the beginning, it's the infancy of an integrated long-term Mars program, but there's a lot of lessons learned here. And now one of the things, hopefully it'll come out, be teased out a little bit in the conversation and the questions, we've been working hard now with the human exploration folks, trying to bring synergy of the two programs together and figure out where there's overlap and leverage. Overlap and leverage between the two, and from one program to the other, both from the existing program we have today to the exploration program going forward, and from the larger exploration program feeding back into the scientific objectives of Mars exploration as a whole. So anyhow, so much for my plug. I'd like to first thank the organization here, Explore Mars, for hosting us and giving the opportunity of this panel to have the discussion. I think we're all very pleased with the fact that you guys are pushing the conversation, pushing the envelope a little bit, challenging the paradigms in order to help get some energy behind the initiatives. That's needed very much, and hopefully this whole community will continue to grow, and the enthusiasm will continue to grow as we go forward. Just a few words here. It's really hard to believe how long we've been working at Mars. It's been, 50 years since the first flyby mission, 40 years since the first lander was launched. And now we have robots on the surface. They've been there for quite some time. Those of you that keep up with trivia notice that the The Opportunity rover happened to complete its first marathon within the last couple of weeks here, an interesting milestone for a program that was supposed to last just 90 days. So it's lasted over a decade and traversed quite substantial terrain there. And we've learned a lot from that process there. We've done some really amazing things, or beginning to do some really amazing things with Curiosity and some of the other systems. Maven's starting to point out some very interesting things about the climate and the evolution of the atmosphere there. But quickly, we're getting to the point that we're ready for humans, assisted by the robots, to dramatically improve the science that we can do, allow us to be much more aggressive in our investigations, and opening up the envelope of what we can achieve at Mars. As the investigations become ever more complex and demanding, the ability that humans supply or bring with their powers of observation and creative reasoning over large distances that they could potentially traverse is becoming crucial for the Mars Science Program. The 2020s, which is the beginning of the discussion of this panel right here, and on into the 2030s, but the 2020s starts with NASA's most ambitious mission, the Mars 2020 mission, which we will send a rover that expand the knowledge of the Martian environment, make in situ observations of its mineralogy and its molecular content and structure, and importantly, take subsurface samples for future return to the Earth, perhaps later in that same decade. These challenging missions increasingly tax us in terms of how do we, and inspire us in terms of enabling the next generation of missions. And that's the source of requirements, the source of discussion, the source of the engineering trades that are going on, and we start to look at the human interaction with the robotic systems and how we can actually expand what can be done both scientifically, engineering-wise, at Mars. Within NASA, there's a number of joint activities underway to accelerate our Mars efforts and to enable the next phase of research at Mars. Within our domain here, the Human Landing Site activity is a joint activity going on now between the HEO folks and between the SMD and the Mars science community, where we're starting to look at what's important for where we go on Mars, and where on Mars would make the mission real, where on Mars brings together all the requirements and all the needs that folks envision for human exploration and scientific exploration. That'll produce results later this year. We've also kicked off a joint strategy effort between the Science Mission Directorate, the HEO folks, and the Space Technology Mission Directorate, where we're working hard to leverage the synergies to buy down some of the risk for future human exploration activities, and where we can merge what we do in the MEP and what's done in the precursor arena for human exploration in order to advance both our scientific objectives and our exploration objectives as quickly as possible. We know that astronauts bring greater mobility, cognitive reasoning, and real-time problem-solving abilities far beyond what we can put in our rovers. So how will that help? And what might that look like? So looking in the crystal ball is part of the job of this panel today. That's the subject. And we got a diverse set of folks here that'll bring both a technical perspective and a scientific perspective to that discussion, and I hope that you'll be free with your questions to stimulate us wandering all over the landscape here in terms of looking forward to what might happen in the 2030s. All right, so let's begin. The way we'll do it is sort of the way the other panels have done it. I'll have each panel member come up and give a brief discussion of their perspective, and then we'll dive into some questions, and we'll open it up to the floor for the remainder of the conversation. So, let me first start, starting on the left here, introduce Charles Wetzel. I had the pleasure of starting to work with Charles when I came on board of the MEP. He currently works in the Program Formulation Office out at JPL, and he's held that position for quite a few years now, since 2009. Previously, he was the Project Systems Engineer for the MSL Curiosity rover. That'd be quite an exciting few years there, Charles. He spent most of the last 25 years working on a variety of robotic Mars missions, and has degrees in aeronautics and astronautics from MIT and Stanford, and a degree in planetary science from MIT. So Charles sort of crosses in the scientific and engineering trade space there, and as you can see, is well grounded with real-world experience on some pretty aggressive and interesting programs. Dr. Melissa Traynor is next. She has a PhD in atmospheric chemistry from the University of Colorado at Boulder, where she studied organic chemistry of Titan's atmosphere and Titan's haze in her laboratory environment. She followed that with some postdoctoral work at NASA in astrobiology, and has been a research scientist at the Goddard Space Flight Center and Planetary Environments Laboratory since 2009. She served on the science team for the Mars Science Laboratory rover mission. So again, you can see how all the paths cross in this community here. She currently works with measurements of the Mars atmosphere taken with the SAM instrument, which is on the Curiosity rover. To her left, Dr. Michael Heck. He was educated, he has a PhD from Stanford University in applied physics, a master's from MIT in physics, and Princeton University, where he got his undergraduate degree in physics. He works at MIT now. He's at the Haystack Observatory, currently the Associate Director for Research Management. And he's also the PI for MOXIE, which is the ISRU payload that you've heard mentioned already in this conference on the upcoming Mars 2020 rover. Previously, he was the PI and instrument manager for the MECA instrument on the Phoenix Mars Scout mission. So a diverse set of experiences there. And all the way to the left, Dr. Ben Bussey. He's a planetary scientist. He's currently the Chief Exploration Scientist at NASA's Human Exploration and Operations Mission Director. He has a physics degree from Oxford University, a PhD in planetary geology from the University of College in London before moving to the States. His research concentrates on remote sensing of the surfaces of planets, recently with particular emphasis on lunar. He was the PI on the Mini-RF radar instrument on India's Chandrayaan-1 mission and the principal investigator on the Mini-RF radar instrument on NASA's Lunar Reconnaissance Orbiter. He's now deeply immersed working with us on the integrated teams between SMD and HEOMD as we examine the scientific motivations and linkages into the ever-evolving plans for human exploration. So we have a lot of relevant experience and recent experience in terms of Mars, in terms of the planning activities that are going on, and we'll now begin to share those. So Charles, would you like to open up?
It's an honor and a privilege to be given the opportunity to share a few thoughts with you this morning. And consistent with the theme of the panel, I'd like to spend a little bit of time talking about ideas and visions about how the nature of our Mars exploration will change across the 2020s as we use the robotic missions to begin to prepare for human exploration, and into the 2030s, once the humans are there, how humans and robots might interact with each other and do the parts of the job that they each do best, and fundamentally change the character of exploration as well. After spending a little time about talking how that'll change in the 20s and how in the 30s, I'd like to close with a few personal thoughts about why we're doing all this exploration and what it means to everybody back here on Earth. So there have been a number of topics that come up in the morning talking about future visions of human exploration. I think some of that was discussed yesterday as well. I want to highlight one specific example in the 2020s where I think there's a thrust or a direction we're moving to get ready for human exploration that has the promise of changing the nature of the robotic missions, and that's the advances in the entry, descent, and landing capabilities that we have. We've since the original Viking landings in 1976, we kind of had to reinvent some of that formula, starting with Pathfinder in 1996 and beyond. And all of those systems have taken advantage of parachutes and inflatable soft good technologies to try to take advantage of the putative atmosphere at Mars. We joke about it being just thick enough to get in the way and not thick enough to really do much of anything useful with. It's becoming more obvious that the parachutes and things like that we've used in the past don't really scale well when we get to the size of the human missions that we're talking about. And although what they're primarily focused on is increasing the mass of the systems and maybe moving from parachutes into propulsive descent. There was discussion this morning about supersonic retropropulsion. when you start moving in that direction, you also pick up the opportunity to get increased landing accuracy. The parachutes are mass advantageous. They're more mass advantageous in the class of robotic missions we've been doing, but it's become kind of our biggest source of error in how precisely we're able to land our systems. There are sensors and capabilities to know exactly where we are, but because we're drifting on the parachute for such a period of time and then only have the propulsion to actually arrest the descent at the very end, we don't really have much opportunity to correct any errors that we're aware of. And going to the supersonic retropropulsion really is going to, I think, enable us to be able to kind of steer out those errors and put our assets down very close to exactly where we need to go. In the case of the human missions, that's because you're landing multiple assets in the same area as other assets have gone before, or you're in close proximity to those assets. In the case of the robotic missions, we're getting more smart about some specific sites we want to go back to and be able to get to those and get in proximity with them quickly. I'll say a little bit more about wide ranging. We want to have mobility once we get there, but this idea to start the mission in close proximity is something that looks very promising, that will be sort of a natural benefit of the collaboration and cooperation. So that's a highlight of a capability in the 20s. When we look forward to the future, the humans arriving in the 2030s, I also see that as an opportunity for humans and robots to cooperate in that time frame. There's a number of different paradigms and models you can think about there. The kind of sensor capabilities and vision systems that the robots would bring to be able to be side by side with the humans and help identify targets and sort of expand their sensory capabilities. I think another thing that we saw in the case of Apollo was being able to implant systems and set things up that could run for long durations. Some of those things that are more tedious or things that robots can repetitively do over and over again. As I was coming through Dulles yesterday, there's a nice display that talked about 25 years of Hubble science. That's another valid model that I think it's important to think about, where you have a very complex system that's been put in place and installed by humans, checked out, make sure it's all working, even repeat visits and servicing and routine checkups, upgrades, and things like that. That can also serve as a paradigm for humans and robots cooperating in science in the 2030s. Whether we talk about long stays or short stays, I think most of the architectures we envision for human exploration would be that they come, they do things, they leave things in place, and then return back to Earth. But being able to take advantage of the systems that they bring with them and operate those remotely, or remotely operated laboratory back from the surface of the Earth could be really exciting view of how science can be done in the 2030s, and we can start to access environments, say the deep subsurface, being able to install large drilling platforms and things like that, which take a lot of interactivity and human know-how to get those going, but then could be left to be operated remotely once the crew has returned back to Earth. So that's another sort of few thoughts about how exploration could fundamentally change going into the 2030s, the things that would be enabled by the presence of astronauts in that time frame. I wanted to close with some personal reflections and a little bit of an anecdote about why we're doing all of this exploration and what it really means. Last Thursday, hopefully along with a number of you, had the chance to participate in Bring Your Kids to Work Day, and so I brought my two youngest daughters with me to JPL as we were going around and touring the facilities. We came to the In Situ Instruments Laboratory where they were testing the robotic arm for the InSight mission that was going to implant the seismometer on the surface of Mars. And my youngest daughter, who's in 3rd grade, says, having a seismometer on Mars is a great idea, because that way you guys can learn, what Mars quakes are like and how you design your rovers to survive them and the landed missions. And I had to kind of explain, it's like, no, it's really more to understand how are Mars quakes similar to the Earth or different than the Earth, what's the core structure like and everything else. And so then her big sister brought her 4th grade wisdom into the conversation. And she said, yeah, it's kind of like when we were in France last summer on vacation. They have McDonald's just like we do in the States, right? and they have Big Macs, but they have a different name for them. So that's kind of the same, and that's kind of different. And then they have all these other like ham and cheese and egg sandwiches, and they even serve wine, and that's just like totally different than anything we're ever used to. And so it really fundamentally comes back to this idea that to appreciate, what's the same everywhere, what's different as you go from place to place, it really requires getting out there and encountering what's new out in the world. So thank you.
First, I just want to thank the organizers of this meeting and for this panel for inviting me to talk a little bit about the kind of science that we can look forward to. Now, since this discussion is about looking ahead to the science exploration of Mars, I just wanted to start by reminding everyone that I think a lot of the goals that drive Mars exploration and science exploration have been pretty constant through time. One of the big questions that we have is, was Mars ever more like Earth? Did Mars ever have life? Does Mars maybe now have life? And while that has been a big constant driver, that the approach that we've taken since we've sort of started visiting the red planet has evolved over time as we've learned more and more. For example, just in my lifetime, the scientific strategy has changed a lot. You know, the Viking rover was looking for maybe a substantial amount of biological activity going on in the soil. And now, instead, we've learned that even just identifying an indigenous Martian organic molecule at the surface really requires a very sophisticated effort. And that's something we've recently done from curiosity, but it wasn't as simple as people may have thought a few decades ago. And so what we've got a lot of knowledge about the Mars environment from what we've learned in the past that's brought us to this point. And we've learned a lot, for example, about the effects of ionizing radiation, about the oxidative properties of the soil. We've learned that we need to probably access the subsurface to really find evidence of extinct or extant life. So really, just the point I'm trying to get at is that our strategy is going to be continuously evolving, and hopefully the discoveries that we make even in the near term will affect that. By 2020, we'll have the new rover, mentioned the InSight rover, geophysical rover. We should have the trace gas orbiter mapping things like methane and other trace gases, which might tell us a lot about places that we're interested in on the Mars surface. And the ExoMars rover is looking for biosignatures and able to access the subsurface in a way we haven't yet. But I'll go ahead and speculate anyway, because that's why we're here and that's what I was asked to do. But I wanted that caveat. So there's three ways I just want to kind of frame this discussion of the science of Mars. One is the scientific exploration for science. Two is scientific investigation for exploration. And three is exploration for science. So the science for science, that's where I live, that's my home, that's where I'm happy. That's pretty much, I think, what we've been doing a lot of in the past in the Mars program. And in that, there's a really strong focus, as I said, is in establishing whether Mars ever was or is currently, at least in some niche locations, habitable. And that's been a big driver for the science exploration. And it will continue to be that going through the 2020s. Jim has already touched on the idea of sample return, and so sample collection and identification with the Mars 2020 rover, and that's obviously going to be a big focus of science in the 20s, because Mars sample return has been identified as really a huge priority by the Mars community, and the highest priority listed, at least in the last community decadal survey. And there's a lot of reasons for that, and I think we can just look to the example of the Apollo lunar sample return, or even just what we can learn from meteorites on Earth. We can do amazing things with in situ instruments. I work for one of those instruments, the SAM rover, but I think the combination of using in situ instruments to analyze the environment, but then being able to bring samples back to analyze them with laboratory instruments with immense capabilities that currently exist, and more importantly, ones we don't even know exist yet. There's so much that, people are still making careers, I think, on looking at lunar samples now, using instrumentation they could have only dreamed of back when they were collected by the astronauts. And so that's the reason that it's been really important, I think, for the community to have sample return, and that's something that we'll be looking to. And there are people here on this panel that know a lot more about the architecture of that particular mission and how that's really going to probably play out when that rover goes, and how the samples will be selected and stored, and how they'll eventually be brought back. But regardless of what the collection or cache strategy is for that, one of the biggest things, I think, for the science community or all of us to think about is, where are we going to go to get those samples, and which samples do we want to bring back? Which ones are the ones that are worth investigating? What we found exploring Gale Crater is one environment we think a habitable paleo environment, and there's likely many more on Mars. And if we're interested in looking for signatures of ancient life, then we'll want to go to environments that have the highest likelihood not only of representing a past habitable environment, but we also want one where there's the highest probability that the evidence of past life could have been preserved. And that's something that we've really learned a lot about in the last decade. And there's a lot of factors that can go into that. And that's something that I think we want to continue looking at carefully is where are those places on Mars? Where do we want to go? And how can we find those types of signatures? And I think that's really going to be a major focus. And that is a really concerted effort that I think is going to keep continuing. It relates to orbital observations, the geological context, everything we're learning about the mineralogy and what we can learn about the subsurface, lessons we've learned exploring Gale Crater and what we've discovered about the types of minerals that are present, the types of environments, and how it impacts the preservation of different types of biosignatures. And so that is where I see a big focus. And again, it's not just a single mission. It's really important to have this integrated set of different types of explorations and also Earth analog studies, whether they're in the laboratory or whether they're out in the field, in, again, understanding how do biosignatures get preserved through, if we're talking about billions of years of time since they were first there. All right, so I've glossed over a lot of other scientific investigations that I think are really important to those of us who work on Mars, but I think that's one that's really going to feed forward into the type of exploration we get. And then I'll just say just a few words on science for exploration. We've heard a little bit about this already, I think, but that's really learning what we need to know about Mars and the Mars environment to safely send humans there. And so there's been a lot of work looking at things like strategic knowledge gaps. Where are there risks that we really do need to learn more about them for them to become acceptable, and we can't just necessarily engineer around them. I don't know a whole lot about all of those, but I know that there's still a lot we need to learn about the atmospheric structure, the climatology of the dust, and that can have a lot of implications, particularly for EDL, as Charles mentioned. I know there's a panel later that's going to go into that into a lot more detail. We're also learning a lot more about the dust itself. As we said, Mars is really dusty. I think we all have seen pictures of it during dust storms. The dust is everywhere. It's going to be unavoidable. It's going to be unavoidable for people that are on the surface. And so if we need to know enough about the dust to know, is it toxic? Does it present a risk to mechanisms, to materials, to things like the life support systems? And then there's also a thought, well, if there actually is extant life on Mars, is it possible that the dust or there are other airborne biohazards? And that's something that we probably won't know necessarily until we actually go there with people. We also need to learn more about some of the types of planetary protection and contamination, I think protocols and controls that need to be in place depending on where we go. If we send humans to Mars to look for extant life in particular, we're going to want to go to places that we think of as special regions where there's the potential of forward contaminating that area. But we obviously, if we're going to look for life, we don't want to bring our own and ruin the whole thing. So we need to understand a little bit more about what is the best strategy for that, and are there regions where we'll have sort of an induced special region just by the presence of the drill or the spacecraft or the humans themselves. And so I think we're getting a better understanding about where are those regions on Mars. They're not necessarily all at the poles. There's a lot of interesting places like the recurring slope lineae where there may be gullies forming at different times of year. And then finally, humans for science. I think Jim already mentioned a lot of the things I wanted to say about that, about the benefit that humans bring to science, so I don't need to review all of those. I just wanted to say there's a lot of reasons to send humans to Mars. I'm all for it. And I think that science is only one of those reasons, and I think we all can agree on that. It's a really important one, but it may not be the only reason. But even if human exploration is not completely science-driven, it is hugely science-enabling, and I think we could argue it has to be science-guided, because that's what brings the huge return to all of us on the planet. Otherwise, it's really just the astronauts getting to have all the fun. I think that anything you want to learn about Mars can be really enhanced by the presence of humans on Mars. And one of the biggest benefits you get is you get a lot more science in less time. You've got that human in the loop. I know even just from Earth-based studies, when it comes to exploring a new environment and choosing the right sample to look at, or having an iterative process of choosing that sample and going back, there's just nothing that beats having a human there. And that's just because of all the great talents that we all have that are inherent to us being human. And I think that's really all I'll say about that. So to conclude, I think we all agree Mars is a really fascinating place, and I think we'll continue to explore with humans or robots, and really, ideally, both humans and robots all together. And I just want to end with this quote that I think just sums up this discussion nicely. I actually pulled this off the website of Malin Space Science Systems, which many of you might know, have provided most or all of the cameras that we've used to explore Mars, at least in the last few decades. Today, we don't know for sure if there is or ever was life on Mars, but one thing is certain, one day there will be. Okay. So, thank you.
Very good.
We're going to do that.
I'll be Michael, not Melissa. I enjoyed Melissa's, referred, as so many of us do, to working on Mars. I mentioned that term to a friend not terribly long ago, and he looked at me blankly and said, "Oh, well, how's the food there?" Honest to God, this really happened. What a perfect setup line. And I was able to turn back to him and said, "The food's not bad, but there's no atmosphere to speak of." So, sometimes things fall in your lap. There you go.
I'll be here all week.
It's a
Don't
good
forget
crowd.
to tip
It's a good
your
crowd.
waitress.
Thank you. Don't forget to tip your waitress. Yeah, I'm going to actually break the paradigm a little bit and start my story not in the 2020s, but maybe back in the 1980s. I came to JPL in 1982, which was the first of 30 years I spent there before I moved on to MIT in my current role at Haystack Observatory. And about almost halfway through that tenure, in the mid-90s was when Pathfinder came along and I think rocked our world in terms of exploring the surface of Mars. Until then, I had spent much of my time working, doing laboratory science. I'm an experimental laboratory scientist, and that's a field where you go in and you build instrumentation and you conceive of experiments and you try them out, you do pilot studies, you improve them, you improve the protocol, you collect many, many samples, you do it again, and then you do it again. And at that point, you're ready to do publication in peer-reviewed journals of science that meets the standard of the international community of scientists. That's how it's done. Those rules don't obtain when we get to Mars, and I'll come back to that in a moment. Mid-1990s, that was when, after Pathfinder, it was clear we could start moving forward to do many things on Mars, including preparing for human exploration. This was recognized clearly by the human exploration parts of NASA, which were called HEADS back then, Human Exploration and Development of Space. And they took a bold step of approving and funding on what was supposed to be the 2001 lander, the first of a series of landers every 2 years to explore the surface of Mars, to approving payloads to prepare on Mars for human exploration. Very public, very visible, and in my mind, with all the studies and even the technology development, the step that really says we have skin in the game is when you're going to Mars to get ready. Those 3 payloads were to address 3 of what we now call strategic knowledge gaps. One was to understand radiation, particularly radiation on the surface, which is different from radiation in orbit because radiation interacts with the surface and makes secondary radiation that you need to understand. That was one of 3 payloads solicited. The second one was to learn how to demonstrate that we can convert carbon dioxide to oxygen. You've heard many people mention MOXIE. I'll come back to that in a moment. But that's a critical step if we want to, in fact, live off the land and use the resources on Mars to help our first crew get home from Mars and all the crews after that. The third one was to continue to investigate hazards other than radiation, and those hazards are primarily in the dust, in the soil, and maybe in the air of Mars. And that's a big deal that I'd be happy to talk about at great length later. Don't have time today. 3 instruments were selected for the 2001 lander to address those 3 goals, and I had the privilege to be leading the effort on the dust and soil investigation, what became called MECA, okay, as a fundamental assessment of all the hazards that the astronauts may face. In the end, the 2001 mission was canceled after the instruments were built for a number of reasons, one being that the loss of Polar lander called into question perhaps the safety of the 2010 spacecraft, of the bus. It eventually did fly as another part of another mission. Another was that the science directorate had perhaps moved on to mobility, and what flew instead was the Wonderful Spirit and Opportunity, the MER mission. And another was perhaps that the priorities had changed within the human exploration program, and those funds were no longer available to pursue that line. So it took a different course. The radiation experiment ultimately flew, not the same one, but similar goals as RAD as part of the Curiosity mission, and it's up there today. And that's a very exciting development. And again, that's human exploration putting skin into the game. The MECA instrument, interestingly, that's an interesting one. I, again, had the privilege to go around again on that. And that flew on the 2008 Phoenix lander to high latitudes where there's both soil and ice to be explored. And it flew as a science payload, as an important science payload. We made really important findings, one being that perchlorate is ubiquitous on Mars, a substance that has significant implications, both good and bad, for human exploration. We got the highest resolution microscope images of Martian dust and soil that we're likely to have until some samples are returned or until astronauts set up a laboratory on Mars. Tremendously successful mission, and the point of emphasizing that is that the overlap, this is not just human exploration up here and science up here. It was the difference between MECA as a science payload and MECA as a human exploration program was negligible. Okay, there's a tremendous overlap in exploring a planet between science and exploration, and that's an important point not to be overlooked. The third payload was what was called MIP at the time, and now is called MOXIE, which you've heard about, ISRU, making oxygen from CO2. And I'm really privileged to be able to now have led 2 of those 3 investigations, to lead MOXIE and to have led MECA. It's a very exciting opportunity. So where to go with that? Well, I want to touch a little bit again on MECA from the point of view of what I said at the beginning about doing laboratory science. We go to Mars, and let's take that perchlorate finding. So after years of development and millions of dollars spent, we had a robot arm that in a couple of weeks could dig a hole about, yay deep. The sort that maybe a 4-year-old with a pail and a shovel could dig in 15 minutes. After that, we took that soil sample, we dropped it in a beaker of water, we stirred it up and put in what's essentially a pH meter and similar sensors for calcium, magnesium, sodium that you could, again, buy in an educational science instrumentation store. A junior high school chemistry experiment. Now, I'm not saying this to put it down in any sense. It was tremendously important work on Mars, typical of the work we do on Mars. We do junior high school science, and it's of tremendous importance. And we don't always do it well. There were many things, if this was the laboratory, I would have redone with that MECA experiment. You can say the same, I'm sure Melissa would say the same for the MSL experiments. Take that instrument apart, clean it up, and do it again, is what a peer reviewer would have said if it was a laboratory instrument.
And they did.
Okay, we get a break on publishing in journals because, for God's sake, this is Mars. What do you expect? But to do the kind of science that meets the international standards for laboratory science, either we need to bring samples back, and that addresses a certain portion of the science you can do on Mars, and only a portion, or we have to have a laboratory there with humans, because it will be a long time before robotic science will ever meet that standard of scientific rigor that is expected in the scientific community. So finally, I do want to end with looking forward and asking a provocative question, I hope one that will lead to some action, and that's the question of where we land. And the reason it's important, you've heard from a couple of speakers, starting with Scott Hubbard and Ollie DeWeck referred to this. We have different resources we can utilize on Mars, and one of the most tantalizing, the one that is the game changer, is water. It's water. And as the Phoenix lander demonstrated, as we knew really since 1966, after a paper by Layton and Murray was published, you go north of 50, maybe even north of 40 north latitude, and I'm saying north because the low altitude is helpful. All you have to do is brush away a couple of centimeters of dust, and there's ice sheets, there's all the ice you could ever want, all the water you could ever want. So I asked someone, a colleague in the HEO business, not too long ago, so why don't we just go there and just do the easy ISRU and the easy human exploration mission, the logistically attractive one? And the answer was, oh, the scientists, I'm putting it in quotes, don't want to go there. Well, there's a lot of science to be done on Mars. The Phoenix mission didn't go to the equator. The Polar Lander didn't go there. InSight doesn't really care where they go. They're doing geophysics. The mainstream missions are going to equatorial regions for a very good reason. Okay, we've heard about the science there. We've heard about ancient oceans. We've heard about life. If you want to study what happened 4 billion years ago, you don't go where there's ice, because ice destroys that record as surely as tectonics and vegetation destroy that record on Earth. Near the equator, you see 4 billion years of history. And if that's your scientific area, that's where you go. Okay, I maintain that for my scientific interest, I want to go to the North Pole and study the climate record in the polar ice. There's many dimensions of science on Mars. So the question is, or maybe the challenge is, why don't we now engage the scientific community, the broad community, not just the seeking signs of life, of ancient life community, with the human exploration community, talk about landing sites, how that affects the architecture of our missions, put it all together and say, where do we go and what technology do we develop to get there? Thank you.
We'll talk about a lead-in. Actually, that activity is ongoing, and there will be a call in the near future for the entire science community to talk about landing sites. But I digress. So when Jim gave us guidance on what exactly to talk about, he said, be provocative. Say something that will generate questions. So what I'm about to say is not my fault. It's Jim's.
Thanks a lot.
Yeah, no, you wait. So we've heard
I'm
a lot
writing
of
down questions for follow-up.
There's been a lot of discussion on the searching for life as the primary science goal for going to Mars, both robotically and with humans. And there's searching for past life, and there's also searching for extant life. Now, this isn't a Star Trek convention, although it's not a million miles away. So I'm sure some people in the audience will have heard from Star Trek the term prime directive. I see a nod. We have audience participation. So for those of you who are younger, so the prime directive, when Captain Kirk wasn't doing adverts for travel things. So the prime directive essentially said in Star Trek that if they found evidence for life, that they couldn't interact with that planet until that life got to a certain level of technology, in the case of Star Trek, warp technology. So what I want to throw out as my provocative question before I come on to what I really want to talk about is, let's say Mars 2020 is driving along and it comes to a rock and the rock moves, or perhaps to be less extreme, there's something growing on the underneath side of the rock. How exactly will that affect our human spaceflight plans? And you can imagine, actually, I hear arguments for two very extreme cases. One is that the money will flow like water once flowed on Mars, and we'll get there quicker. I don't mean it evaporated and went away. No. That we'll have enough money to essentially go to Mars as quickly as possible in any way, shape, or form that we wish. The other scenario is just as extreme in the other direction. Will we get a do not enter sign? Will we get that you will not be allowed onto the Mars surface with humans until A, we've studied it out the wazoo so that because we know we're going to affect it once we go down with humans, or you've got what is referred to the War of the Worlds scenario. Will the general public say, we don't care how well you studied it, we don't believe you, you're never going down and bringing back? And I think there's your provocative question. Yeah. There you go. I live to serve.
Supposed to bring answers.
Page 2. No, so as I thought would happen when I realized I was going last, others have discussed in good detail some of the activities that will go on in the Mars surface in the 2020s and 2030s. What I wish to do briefly is discuss some of the activities that will occur closer to home, particularly in the 2020s, that will, though, help us get us to Mars. You heard from Bill Gerstmeyer, the AA for HEOMD yesterday, as well as, to a large extent, the previous panel. The NASA way of getting to Mars is the Evolve Mars campaign. The idea is to get to Mars as part of a sustainable campaign into the solar system. Mars is it's an important destination, but we're not doing Apollo to Mars. As directed by the president, we're expanding into the solar system with people, of which Mars is a significant goal. And again, as Mr. Gersmeyer said yesterday, that currently equates to having humans in cislunar space. So post-station, we will have humans in cislunar space in the 2020s. And I want to talk about some of the activities that might be achieved by those humans that actually help us get to Mars or help us be more efficient once we get there. Now, NASA is thinking about a habitat in cislunar space as well as the asteroid retrieval mission, whereas our international partners and commercial are thinking about lunar surface, and they all play well together. You know, even for the case of ARM, NASA is looking at a very high-power solar electric propulsion system to conduct that mission. You know, once that level of SEP has been demonstrated, that's out there then as a technology that we might choose to use to send larger payloads to Mars to conduct science and other investigations. But I think a large benefit of if we end up having humans in cislunar space in the 2020s is learning how to efficiently do human robotic exploration. Now, there are many examples on once we get to Mars with people where we will want to conduct human robotic exploration. We heard the discussion of special regions, and that we'll want to very likely explore regions that look most promising for past life. We don't want the dirty humans to go contaminate that. And I don't mean that facetiously. I think one of the actual large unknowns is we don't know how dirty the humans will be once we get there. We don't know. Can they go 1 meter away from this special region, 100 meters, 1,000 kilometers? We don't really know, and I think that's a key point. So we're definitely going to want to do exploration of those regions using robotics controlled by humans. Now, those humans might be either in Mars orbit or on Phobos if we end up going there first, or even if they're on the Mars surface. You can imagine several scenarios where you will want to expand their reach to further afield than they can safely go because you're going to have some return to ascent vehicle capability by doing robotics. I mean, actually, a side issue that I thought of as the discussion, one other issue of those special regions, and Mike sort of touched upon this, is those special regions are also the places that have the resources that we might need in order to do a sustainable campaign. So that's sort of a provocative light question that you can cover if you wish. So one opportunity on the lunar surface, once we have people in cislunar space, is to learn how to efficiently conduct human robotics so that when we go to Mars, we have all the protocols, we know the processes, we know how to do this well, and that's one example of things that we might want to do. Think of it as potentially even a special region dry run. Another example would be a human-assisted sample return. There are a couple of benefits to this. That you learn how humans direct the robot to pick the correct sample, something that obviously we're going to learn also with Mars 2020, but also some of the systems operations. Some of the Mars sample return scenarios actually have those samples coming back into lunar orbit and having the humans capture them. So those are also technology techniques that we could practice. Then there's the issue of lunar resources. If our international partners go to the lunar surface or the commercial, it's very likely that we know from orbital data that there are very likely significant water deposits on the Moon, particularly in the lunar poles. We don't know the physical or chemical form or the actual lateral or vertical distribution. It's a resource. Those are key pieces of information that we will likely glean in the next 10 years if we have lunar surface activities by our partners. And as we heard this morning, the MIT study talked about, they determined that lunar resources are valuable. Their current model uses the molten volatile extraction technique. If there are water volatiles which are easily extractable, that's even more efficient and both in yield and the amount of power required than molten volcanic approach. The other thing that will happen with lunar surface activities is learning. We can potentially test long-term Mars ISRU equipment. How well does it cope in a dust environment, in a low-gravity dust environment? Just what breaks? If we can learn first-order problems with such equipment now, then that helps us design better equipment that the crews are going to rely on. But also sort of secondary effects like, we generate hydrogen and oxygen. For a long-term Mars program, you've got to learn how to store those incredibly efficiently. You want very low boil-off, and there's nothing better than actually doing that to learn what works and what doesn't. So in conclusion, there'll be lots of interesting science done on the Mars surface in the 2020s and before people arrive in the 2030s. But we'll also be doing interesting things closer to home that will help us on the journey to Mars. Thank you.
All right, let's try a few questions here. I think you heard a diverse set of comments on what might happen, what might be the challenges, what are the possibilities there. And I think from that, at least I derive, the conclusion is it's not robotics or human, it's going to be a mix. And what is the right mix? How do they complement each other? And there's a couple of areas that I thought I'd just start you with a couple softball questions and throw out there is the most sophisticated lab on Mars to date is the SAM instrument, which was quite a development program in and of itself and quite an accomplishment to actually run it. And we're starting to see the results from it there. But as we develop any flight hardware, that sophisticated or less, there's a time period associated with that. So pick your favorite number of years, 5 years, 10 years, whatever, to develop that, and then the actual execution of the mission. So by the time we get to use it, not only is it a zillion miles away and we're operating robotically, it is somewhat out of date from the technologies that have evolved in the labs on the surface of the Earth. One of the reasons for the Mars 2020 mission and the continued desire to bring samples home, even though we're starting to do analytical work on the samples at Mars, is we now know that some of the more sophisticated analytical techniques that have been evolved from molecular biology and et cetera will continue to evolve, and that diversity of instrumentation, it's difficult to envision keeping up with it and getting it in the field. Where do you see the line between what the crews will be able to do once they're there, bringing their intellect and cognitive powers, and perhaps the larger labs that would be in a habitat, with this paradigm that the science continues to progress here on Earth? Do you see need to continue to bring samples home, continue to do a mix of the scientific work in the field as well as back here in the labs? Any comments?
Well, you should start.
Yeah, I'll start. I think it's got to be a mix, absolutely. I think that one of the most important things with selecting samples to bring home, even if astronauts can bring home a lot more sample material, hundreds of kilograms versus grams we might get from a sample return mission, either way, you have to bring the right samples home. That's going to be a very valuable resource. And there's a lot we learn. I heard this really interesting talk yesterday, actually, about dating impact craters. And doing it on Earth is challenging, extremely challenging. And that's when you've got a lot more resources available to when you're out in the field, even just selecting the right sample so that you're getting the date of that impact versus getting the date of the formation rock, or actually what happens is a huge amount of samples in between because you get partial release of sort of the thermometer you're testing for. And it was a really great talk about how when the astronaut, for example, I just extrapolated to Mars because that's where I thought it was a good analog for, is looking at the types of samples. You need this interplay between where the samples are, choosing where the samples need to come from, let's say in that crater or that environment you're in. Then you need to be able to look at it very closely, microscopically, in a laboratory, which would be, you would think, on Mars, to start to look at, is this the right sample that's going to get me the information? Even if that really final step of analysis is best done on Earth, there's so much analysis that needs to be done, I think, sort of as an iterative process as the samples are collected and the environment is explored to make sure that the correct samples are chosen to get at the science that we want to get at. And so I think that no matter what the architecture is of humans versus robots, I think we're gonna want that to move in parallel, and there's going to be certain investigations that are best done by the astronauts on the surface, but there's still going to be the goal of sample return. But I don't think you just want to grab samples and run. We're hoping our astronauts will have a lot more time on Mars than the Apollo astronauts had on the moon, right. and that there'll be a lot more time to really explore the environment and collect the right
So is it safe to say you're saying the explorative power that the crew brings to find the right place?
Oh, absolutely. I mean,
identify
there's
the right samples,
absolutely
is the huge magnifier.
Huge magnifier, having that human being in that cognitive loop, that quick determination. There are some things that I think that humans are really best suited for, and I do see that's a huge advantage. And I think I really liked also the discussion of instruments that the humans can set up but then leave behind as long-term monitoring stations. I think that there's going to be a huge interplay with all of those capabilities, as opposed, I don't think anything should go away.
I can add to that a couple of scores. First of all, just a reminder that while we can do a tremendous amount with sample return, we can't study meteorology with sample return. We can't study geophysics with sample return.
Right.
We can't study atmospheric chemistry with sample return. It is a window into Mars, and an important one. But I don't want to diminish all those other sciences that humans can explore, including getting access to samples that our robots just can't reach. I don't believe we're going to send a capable drill, for example, that will come close to an astronaut with a shovel in the foreseeable future. Also want to make a point about what you mentioned, SAM as the most sophisticated laboratory we've built, which certainly is true, and at tremendous cost. But most of this cost goes into robustness and it goes into autonomy. You could, in a laboratory, buy a mass spectrometer with hundreds or thousands of times the resolution of SAM, which would be of great value if we could fly it. That's not where our investment is going. Our investment is going into making it work, and making it work in very, very low power. If you have a human scientist running a laboratory, you can send far more sophisticated equipment, even if that equipment needs some maintenance and upkeep. You can do sample preparation properly and not just sample investigation you've imagined you'll need, but in fact sample preparation that's optimized for the samples you find. You can have power. I mean, a side effect of sending humans is that we'll have robust power systems. We're running the whole darn rover, and we commented earlier, there's light bulbs that are blinding us, have far more power shining at us than the entire Curiosity rover. So you bring humans, you'll have a laboratory, you'll have a power system, and you'll be able to do science that just will leapfrog anything we can do today despite the sophistication of our robotics.
Good point. Thank you. Charles, you mentioned there's probably huge derivative value in some of the technologies that will be needed for human exploration. For example, you talked about the ability to prove the accuracy on our landing. Can you describe how that, if we could land much more precisely, would allow us to complete the sample return activities in a different way?
Sure, that's an area where in the past when we land, we're exploring a broad region, we're trying to characterize it and go from place to place. And landing accuracy, as we move forward, particularly if we're retrieving samples that have been collected and characterized, identified by a prior mission that roved over a wide area but brought them together in one or a couple of locations. It's moving into this domain where there's a specific objective. You want to get down, accomplish that objective on the surface, and then get back off. And even though that's a very different application than a future human mission where you're building up this infrastructure over time, or you're going to one place and putting a certain asset down and then coming back to it over and over again, they both have this characteristic of knowing where you want to go with a high mass system and getting that on the ground where you want to do, and then be able to fan out and explore from that. And so these questions of deep drilling rigs to get deep below the surface and those sort of things, you're not going to want to, you may want to move them around a little, but you're not going to want to land kilometers away from where the site of interest is going to be. And similarly, bringing this next generation power systems, next generation laboratory type capabilities that we expect to come along with the human explorers and put those in place. You want to be able to put them down close to whatever criteria it is you use to choose those landing sites. So.
Thank you. All right, shall we open to the floor?
Most of the human architectures we've heard described over the last few days have focused on building infrastructure at a single site on the surface. I was just wondering if somebody on the panel could talk about the trade-offs between human exploration at a single site, even with some mobility, versus the ability to land astronauts at multiple sites around the Mars surface.
Ben, maybe you could bring in the mobility work that's
Yeah,
been going on in the studies.
I'll take that. The reason that the Evolve Mars campaign is thinking of exactly that, and I want to just expand on something that Charles said, is we're looking at an exploration zone where an exploration zone is its size is defined by the expected mobility capability of the crew. And right now we're looking at something of the order of 100 kilometers is what we would expect the crew to be able to go radially away from sort of the habitation lab area and then come back. So the goal is to look for exploration zones that contain sort of the most scientific regions of interest where you cover a whole range of science within your exploration zone. The reason that you want to keep going back to the same site is, this is, as I said at the beginning, this is not Apollo to Mars. This is part of a sustained exploration process. And that means eventually you're looking to be able to have crews there for longer and longer periods of time and eventually become as close to self-sufficient as possible. And to do that, you do that much faster if you build up infrastructure in one place. And that gradually you will expand your reach to all of Mars. You take that, compare that to the Apollo model, where you do 6 missions, you keep 6 groups of scientists happy, to be slightly facetious, at 6 different locations, and then you're done. The goal is not to do that. The goal is to build up capability so that you can explore where you want, when you want.
If I could just pick up on that and also tie in something that Michael mentioned as well, is there's sort of these competing objectives that are driving these exploration sites to sort of 2 different classes of terrain. One of them is the places that are the ancient Mars with the dry, preservation potential. I guess Melissa mentioned that as well, where we can really look back towards signs of, did life ever arise on Mars back when it was a lot wetter, presumably had a thicker atmosphere and so on, versus the areas that are more ice rich, that have weather, that have active processes there. Those don't tend to happen exactly in the same place, but the greater the mobility with sort of a central hub plus spokes exploration strategy, as Ben was describing, is an opportunity to really satisfy both of those interests. If we could have a base camp near the resources with a high power system there that can take energy out of a reactor and put it into breaking these chemical bonds to make fuel or oxygen, those sort of things, but have it close enough in proximity to these archaeological sites like the Olduvai gorges of Africa and so on, where you've got the historical record laid down. Getting that commuter distance, either making it short or having good mobility capability to go back and forth between those 2 things really could let us have our cake and eat it too.
I can add one short point. We didn't build McMurdo Station in Antarctica in the most scientifically interesting spot in Antarctica. We built it where it would be most logistically justifiable and accessible.
Yeah, one other follow-up, and also the crew safety aspect. By going back to the same site, there's an efficiency that you don't need to take 2 of everything, but sometimes you will have redundancy because if something breaks, you might well start to build up spares, as opposed to if something breaks, they have to leave and come home.
Okay.
I have a question. Assuming that we're going to land humans on Mars mid-2030s, then by the mid-2020s, we have to have decided where we're going to be sending them. And so our robotic packages should be sent to that spot to gather the data that's necessary to inform the design decisions on the habitat and the power systems and the spacesuits and the rovers and the ISRU systems. So it seemed to me that what you send needs to be designed to be used by the humans when they arrive. And so if you have a rover, you want to be able to telerobotically operate that rover from the habitat. If you send science packages, you want them to be something the astronauts can move around and deploy. Maybe you want to send a rover that has a trailer hitch on it, and you send a package that consists of a rack of science experiments, and the rover picks off a seismometer and a MET package and something else, puts it on the trailer and deploys them. But when the astronauts arrive, they'll be able to redeploy them. So I'm just wondering, if you're thinking in terms of that kind of architecture where the science packages are usable by the astronauts, redeployable by the astronauts, maybe dependent upon the rover for communications and power, mobility, a robotic arm to operate them. I mean, you could even have just a drill on wheels that it tows somewhere and provides the power to, that sort of thing.
I think we're thinking of those thoughts. If they last that long, that would be great. It's a little tricky to make sure if you're really counting on it being there, you might design it a little bit differently. In terms of being operable by the astronauts in general, as we send robots there today, we're designing them to be operated all the way back from Earth with these long light delays and everything else built into them, and to be totally, have the redundancy and the fault detection and everything built into them. That, to first order, that job only gets easier if the person operating them is 10 feet away than if they're on the other side of the solar system. So we're definitely taking that into consideration. I think another thing too is that sometimes when we talk about learning what it is we need to know about the landing site that we're going to go there. The ground truth of getting down to the surface of Mars and making those measurements is very expensive. And the strategy we've had to date in the scientific directed activities is the first step is to do the global reconnaissance at the spectral ranges, at the resolutions that you really want to know for the characteristics that you care about. And then we've got a lot of the data sets now that should help inform picking a good landing site for future human missions. But our sense is that as we start really thinking through that problem, there'll be other measurements and other data sets that are important to help pick those landing sites. And our sense is that we need at least one more orbital mission that's really tuned to the measurements that are needed to first pick a landing site or pick a candidate landing site early in the 2020s, so that then we can go in the mid-2020s and get ground truth at those landing sites.
So maybe the first step, you asked the question of, do we know what we're going to run into at these landing sites? And then you went on to talk about what that might mean. So for that reason and others, we've started this activity this spring to start identifying candidate landing sites for the human exploration activities. And the intent as we work through this over the course of the remainder of this year is once we narrow that down to a handful of sites and the strategies on how the crew might be deployed, the exploration zones that have been mentioned, is then we'll take our assets that we have for the high resolution reconnaissance and we'll actually image those. And we'll get the information back about those zones, and that'll be a feed-in set of data to the engineers and the architects as they work through their plans and their thinking to go forward. It's important to keep in mind that even though MRO has been there for, the better part of a decade, we've only have high-resolution imaging of maybe 1% of Mars. And the issue isn't so much the camera as the issue is the data back home. And one of the reasons that you often see us talk about infrastructure and keeping infrastructure fresh and current and with redundant assets in place is because just in doing a robotic exploration program, we've seen the dependency on reliable infrastructure to do what we do. The MRO is used exclusively to do the forward planning for what we do with our rovers. We do the reconnaissance in the area to help the planners for the next week's set of treks that we have to take. And so a very important element of the problem is, as some folks mentioned in the earlier session, logistics is a big part of Mars exploration as well.
Jim,
Go ahead.
could I add one more small comment on that pertaining to ISRU, which is that, for those of you that are early adopters for electric cars, you know all about range anxiety. Having the ability to make a fuel, at least with today's technology, as opposed to having large batteries in a rover that are, heavy batteries that are limited in range, I think has a profound influence on the degree to which the astronauts will be able to travel from the base, to distant places. So that's worth consideration.
I have a question along the lines of your question regarding the prime directive. Let's say we land humans on Mars and we get there and we do a little bit of scanning and the ice right below the habitat has life in it. What effect does that have on ISRU, on the mission as a whole? How would we deal with that?
Is Cassie still here?
I thought Mike was going to say bring good filters to make sure.
Yeah.
No, I don't think we know. I think it would be useful to have protocol, and Cassie touched upon this yesterday, to have protocols in place for certain scenarios. That's quite an extreme scenario, but I think having protocols for for certain scenarios ahead of time would be good, because you don't want to be wondering what to do once you're there. You want to be able to react to what you find.
Of course, the good news is if you find microbes in the ice right below the habitat, they're everywhere on the planet, so at least you don't have to worry about wiping them out. It's more a matter of understanding impact on the mission itself.
So I think, I think it's a great question. It's the, first of all, it would be the discovery of the century if we did that. So first of all, I think the folks would be applauding across the globe and amazed at the discovery. But it points out the fact that at least the early human missions, they're going to have to deal with strict quarantine and control protocol for the crew and everything that they do and all the planning that they do. And I don't know that we have gotten to the point of really looking into that in great detail and the understanding of the implications of what we do and how the crew goes about doing its chores. But it's one aspect that makes the design very challenging.
We should emphasize it's an extraordinarily unlikely scenario from everything we know about Mars today. Absolutely, absolutely.
All right, how are we doing on time?
You have about 5 minutes. No.
And that ends our
5 minutes ago.
If you've got good questions, you've got 5 minutes.
That's a high, intimidating.
I think you put a damper on things.
We're competing with.
Here comes some.
Okay.
Thanks. Let's thank our. Okay, so the last announcements of the morning. Folks who have got luncheon reservations, hustle your bustles is the polite way to say move your asses down to the City View room. I'll give you, it's easy to get to. There were maps that were handed out in the package that you got. Easy to find. This is a grid. The streets are laid out as grids here. If you move quickly, reasonably quickly, it's about a 10-minute walk, so you ought to be able to get there just fine. For those folks who are on in the afternoon, please, please note, folks, that now the afternoon sessions split in two. I think there's one that's going to be in here and another one that is, back? In 309. So, and you can go back and forth to whichever ones you want, but please note that there are two separate parallel activities this afternoon, which begin at 2 p.m. sharply. So any other questions, announcements need to be made, or whatever? Okay, thank you all.